Greetings to all. Myself Vaishnavi, Assistant Professor, IT Department from SNS College of Engineering. Now we are going to see about the virtual memory in operating systems. Virtual memory. It is a technique that allows the execution of the process that may not be completely in main memory. Next one, advantages. Here we have the four advantages that allows the problem that can be larger than the physical memory. Second advantages will be the separation of user logical memory from the physical memory. Third point, it allows the processes to easily share the files and the address space. Fourth point, it allows for the more efficient process creations. Next one, virtual memory can be implemented using the demand paging and the demand segmentations. The demand paging. It is similar to the paging system with the swapping. Second one, demand paging. It brings a page into the memory only when it is needed. To execute the process, it swaps the entire process into the memory rather than swapping the entire process into the memory. However, we use a lazy swapper. The definition for the lazy swapper will be never swaps a page into the memory unless the page will be needed. Here we have the advantages. Here we have four advantages, that is less input output needed, less memory needed, and the faster response, and then more users. Next one, basic concepts. Instead of swapping in the whole process, the pager brings only those necessary pages into the memory. Thus, it avoids the reading into the memory pages that will not be used anyway. Next point, reduces the swap time. Third one, reduces the amount of physical memory needed. Next point, to differentiate between those pages that are in the memory and those that are in the disk, we uses the valid and the invalid bit. Valid and the invalid bit. The valid and the invalid bit is associated with each the page table entry. Here we have valid associated page is in the memory. In invalid, it is an invalid page, and the valid page but it is currently on the disk. Next will be the page fault, that is access to the page marked invalid causes a page fault trap that determine whether the reference is a valid or invalid memory access. Next point, if the references is invalid, then terminate the process. Third one, if the reference is the valid, then the page has not been yet brought into the memory. Fourth point, find the free frame. Fifth one, read the desired page into the newly allocated frame. And then sixth one, reset the page table to indicate that the page is now in the memory. And the last one is restart the instruction that was interrupted. Next one will be the pure demand paging. Never bring a page into the memory until it is required. We could start the process with the no pages in the memory. Second one, when the OS sets the instruction pointer to the first instruction of the process, which is on the non-memory resistant page, then the process immediately falls for the page. Next point, after this page is brought into the memory, the process continue to execute, faulting as necessarily until every page that it needs in the memory. Next one will be the performance of the demand paging. Let P be the probability of the page fault, that is 0, P to 1. Here we have to calculate the effective access time is equal to 1 minus P, that is probability, int MA plus P into page fault time. Here we have the MA as the memory access, and P is the probability of the page fault. Next one, the memory access time denoted MA in the ranges from 10 to 200 nanoseconds. If there are no page fault, then EAT, that effective access time, is equal to MA, that is memory access. Next one will be the page fault causes the following sequence to occur. Trap the OS and save the user registers and the process state. Next one will be determine that the interrupt was a page fault. Fourth one, check whether the reference was legal and find the location of the disk. Fifth one is read the page from the disk to the free frame. Wait in a queue until the read request is serviced. Wait for the seek time and the latency time and transfer the page from the disk to the free frame. And then while waiting, allocate the CPU to some other users and then it interrupt from the disk. Save the register and process state for other user. Determine that the interrupt was from the disk and then reset the page table to indicate that the page is now in the memory and then wait for the CPU to be allocated to this process again. Thank you.